I should say I made a mistake on my first slide, so that's a good start. I think pretty much everything that I'm going to be talking about today is joint with Alex Blumenthal, who was recently a postdoc at Maryland and is now tenure track at Georgia Tech, and Sam Punchin-Smith, who was a graduate student at Maryland and is now a postdoc at Brown. So the whole, pretty much pretty much everything that I'm talking about is joint work with them. Okay, and I mean, of the work, that's ours that I'm going to be discussing. Okay, so the day is, the course is split into 3 days. So the first day I'm going to give kind of an overview of statistical theories of turbulence. And I'll make that a little bit more precise what I mean by that. And then specifically I'll talk about passive scalar turbulence, which is kind of, at least in what's called the bachelor regime, is the simplest case that you would see in a simplest case that you can observe in nature. You can construct toy problems that are simpler, but sort of something that appears in nature. This bachelor regime passive scale turbulence is the simplest example. So I'll give an overview also of that. And then I'll state sort of our main result on that topic, probably at the end of the first hour. And then the next 2 hours will be sort of a very overview, kind of long-range summary of how that result was proved. So the first day I'll prove something called, these are days, these are actually hours. Hour. So the second hour I'll prove something called Lagrangian chaos. And the third hour I'll prove something called exponential mixing. I'll explain all that, what that is. Okay, so I do have to assume some basic knowledge of semi-linear PDEs, some pretty basic probability, but also some stochastic calculus. So I hope that you guys know something about stochastic PDEs. I will try to keep the talk kind of not very technical, so keep it at the level of intuition. So if you even have a vague idea of stochastic calculus and stochastic PDEs just from an intuitive level, and you don't remember what the definition of a filtration is or whatever, like that should be fine. So because I'm not going to give the rigorous mathematical proof, so there's certainly not enough time for that. I just want to sort of give an intuitive sketch of how everything's working. And similarly, the actual proofs use a lot of Malevin calculus, which is very interesting and it's not as hard as it sounds, but still too much to discuss in these 3 hours. So, when you go to look at the papers, or if you go to look at the papers, then you'll see it there. I won't get into it too much. All right, so what is turbulence? So basically in 2017, a bunch of postdocs and grad students and we sat down and we wanted to understand what actually is turbulence from how a physicist would understand it. And it's quite common. It's not specific to fluid mechanics at all. It's actually some version of turbulence is almost ubiquitous in a sort of general class of systems which are infinite dimensional and weakly dissipative, and the nonlinearity has to be somehow of a certain type, which I won't make too precise, but I can speculate. But let's just say that fluid mechanics, plasmas, nonlinear waves, all of them display some variation of turbulence, and many of them display multiple different types of turbulence. The most classical case that's studied in physics, and in some ways the easiest potentially, is actually when you subject the system to an external driving force, and you first send time to infinity. You settle it into what's called a statistical steady state, and then you send the dissipative parameter nu to 0. And you want to understand the statistics of the system in the limit as nu goes to 0. So, so what are some basic properties that are shared of essentially all turbulent systems? So one is some kind of chaos. So this would generally mean positively Lyapunov exponents, and I'll explain what that is because that's going to be important for our study. This though, so extreme sensitivity to initial data. So this means that if I subject the system to the same force, but I slightly change the initial data, I get a very different answer, kind of exponentially fast, for example. This isn't an infinite dimensional thing. This is, you can observe it in 3x3 ODEs just fine. But something that is infinite dimensional is the multi-scale nature of turbulence. So what happens, and I'll explain this in more detail, is that this forcing generally acts at sort of one set of scales called the injection scale or the integral scale. And that the energy that it puts in spreads out among all the other scales. available in the system, roughly speaking. It spreads out. So for example, if the dissipative operator is something like a Laplacian, then what can sometimes happen is that the injection scale is a sort of scale 1. The nonlinearity kind of mixes everything up and sends information from low frequencies to high frequencies where the dissipation is very strong. And so even though nu is going to 0, the effect of the dissipation is never vanishing. So that's this multi-scale nature. One other thing is universality. This is what you see. So this intermediate range of scales where the nonlinearity is dominant is usually called the inertial range, at least in fluid mechanics. The statistics in that range are universal in the sense that it doesn't really depend on what dissipative operator you use, and it doesn't really depend on what the forcing is. This is what's observed. Okay. So it doesn't matter if the wake is behind a Honda Civic or a Lamborghini. All that really matters is how much total energy is involved. Other than that, the statistics are basically the same, regardless of what kind of car you're looking at. That's what you're kind of looking at there. And then the last property is something more specific about the inertial range, and this is common to all turbulent systems, which is that you get a constant on average flux of conserved quantities through the inertial range. So energy will be fluxing through one scale to the next scale, kind of flowing from one scale, from large scales to small scales at a approximately constant rate. So on average, constant rate. So like you dump in 1 energy per unit time, and then that energy flows through all the scales, and then it's dissipated at the dissipative scale at that same constant rate. So no matter how small you pick the parameter, the sort of amount of energy being dissipated is the same at all times. Again, on average. This is what it looks like in 3D fluid mechanics. So this would be the 3D incompressible Navier-Stokes equations. So here's a simulation of a wind farm. And here's an actual smokestack where you can visualize the kind of crazy turbulent dynamics by the smoke. And you can see that it's very multi-scale. So you have non-trivial features at this scale, non-trivial features at this scale, non-trivial features at this scale, and so forth, all the way down until kind of finally the viscosity will take over. And of course, the general shape of this shape of this plume depends on the specifics of the smokestack, and it depends on actually the background wind. But the statistics at these smaller scales don't depend on the smokestack or the wind. That's what I mean by universality. So it's not so the details don't depend. That's what we observe. And so here is plots of some of the most important statistical quantity that you want energy. You want to understand, for example, how does the kinetic energy distribute itself through the inertial range? And so these are log plots of what the physicists call the power spectrum. So that's the energy density as a function of frequency, scaled by dimension -1, or multiplied by k to the dimension -1. So here is actually an experiment of the energy spectrum measured coming off of an airfoil. So they have like a wing, and they're looking at the turbulence in the wake of the wing. And you see that the details of the experiment, so the details of the external forcing, change very much the details of the power spectrum here. So this is kind of the injection scale. And then this is the inertial range where you get universality. So remember, this is a log plot. So this is energy, or log energy, and this is log frequency. So the straight line means kind of like Sobolev type regularity, or Holder type regularity in this case. It's like, and so what you observe in 3D Navier-Stokes is that power spectrum is approximately -5/3. So that's what we observe approximately, though it seems like there might be deviations to it, but we just don't know for sure. This over here is amalgamated data from a bunch of different experiments, all kind of normalized and put on the same plot. And you see that, in the injection scale, there's no universality, of course. And then you see in the inertial range, this Kolmogorov -5/3 power spectrum. And then you see a dissipative scale where the dissipation dominates. So that's what you observe. In 2D fluid mechanics, or approximately 2D fluid mechanics, you see something very different. So this is actually a plot of the vorticity field. So if you're not familiar with fluid mechanics, that would be the curl of the velocity, which in 2 dimensions you can think of as a scalar. And you see it has a sort of large scale organization to it that these flows seem to lack. And that's very important. And similarly here is actually data from the ocean. These are different temperatures, water of different temperature mixing the ocean. And you see kind of large scale features that are quite distinct and relevant on very, very large scales. And that's because in 2-dimensional fluid mechanics, energy goes energy goes one way and something called endstrophy goes the other way. So what happens is that if you inject energy at scale 1, then you have actually energy is going from that scale 1 up to larger and larger and larger scales until it's actually capped by the scale of the system, which is why you get, in atmospheric flows, you get huge hurricanes kind of on the scale of continents, things like that. Whereas in more 3-dimensional dominated flows, you don't get this kind of coherent structure. So that's called an inverse cascade. And you also get a direct cascade. So you also get not energy, but entropy cascading from order 1 scales down to small scales. And so I just wanted to include this to see like what is universality, and also to show that not every turbulent system is the same. So the exponents depend very much on what system you're looking at, and the whether or not you see 2 cascades or 1 cascade depends very much on the system that you're looking at. And yet a lot of properties are kind of universal. So there's lots of let's say common threads between different turbulent systems. Okay, so what I'm going to talk about is statistically stationary turbulence, which is kind of the classical case. So you want to think of this as a system that is kind of in equilibrium in a statistical sense. So think of like wind over a sail or like water over a stone in a river. And what you observe is that the stationary statistics don't depend on the initial data, and that if you look at one experiment and compute time averages, you get the same thing as if you run many, many experiments and average them. So ensemble averages are the same as time averages. And so what we should be looking for is an invariant measure over phase space. So you have phase space, which is the state of the fluid. And you want to find that a measure mu, where if you randomize the initial condition, then this law doesn't change as a function of time. So if you randomize with respect to mu, then the solution always has a law with respect to mu. The individual trajectories are moving all around, just like wind over a sail. But statistically, somehow the statistics aren't changing as a function of time. That's the idea of this. And then you can compute what an ensemble average is by just integrating with respect to this measure. And then you want this measure to be ergodic in the sense that you want initial conditions the time averages of all initial conditions to trace out ensemble statistics. So this is what you kind of want. And you want this to be true for generic initial data, whatever this might mean, because in the truly turbulent regimes, it doesn't matter how you start off the system. That's a little bit of an overgeneralization. There are some counterexamples to this. But generally speaking, in the really turbulent asymptotic regimes, the initial condition does not change at all. Does not change the answer. So you want sort of all initial conditions to give you the same answer. So even for kind of like 3-dimensional ODEs, the construction of such invariant measures is almost impossible in practice, with some small exceptions. And so that's one major motivation for moving to random systems, because even sort of the basic thing is the study of these measures. And we're kind of light years away from being able to do this for a PDE like the Navier-Stokes equations. So I think I'm very convinced that you cannot do the deterministic case if you do not know how to do the random case. And so we're going to be talking about the random case. And so I'm going to be studying the stochastic Navier-Stokes equations. So this is stochastic PDE, a really nice stochastic PDE, at least in 2 dimensions. So this is the time derivative of Brownian motions that we're going to add in to force the system, and we're going to put it on the torus like this. Now, all kinds of external forcing of this type are a little bit non-physical. Real systems you mostly drive from the boundary. So deterministic or random, if you're studying sort of body forces in a periodic box, you're already kind of a little bit outside the regime of exact physics. But it's observed that doesn't change the statistics in the inertial range. So physicists have observed this hundreds of times in numerical simulations. And again, this goes back to universality. It doesn't really matter about the details of the experiment. So the hope is that at least in this idealized regime, we can understand turbulence and then go to understand more complicated problems later. So these E's are Stokes eigenfunctions. So they're just divergence-free Fourier modes, essentially. And occasionally I'll use time shift on the Brownian paths. So every random path, so every omega is a kind of realization of these Brownian motions. And these Brownian motions, they're sort of time shift invariant in law. So if you time shift, it's the same as starting at time 0, essentially. So that's what this time shift is. Now, to understand this equation from the standpoint of a stochastic PDE, you generally use the mild form. So you get rid of the pressure, or you rewrite it to sort of include the pressure on this nonlinearity. You have this nonlinearity, and then you have this stochastic convolution. So I'm using additive noise, so it's the theory is much simpler and standard. In 3 dimensions, solutions could break down to our knowledge. We don't know. I'm not going to be dealing with stochastic weak solutions. That our theory does not apply to that. So in 3D, everything I'm going to say works in 3D if you use hyperviscosity. So if you use enough dissipation. But I'm going to just keep the 2-dimensional case, just to fix one set of numbers and work with that. Now, and I'll discuss a little bit. I'll also take forcing, which is supported in every mode, or at least has to be supported in all sufficiently high frequencies. You should think of alpha as just large. So you shouldn't think of it as 5. You should think of it as like 27 million. But it's not infinity. Okay. So you think of the solution as being like 1 million times differentiable, but not necessarily 2 million times differentiable, something like that. And then I'm going to study the evolution of the system in this phase space. And I'll explain why I need to take this type of noise for now, later. It's pretty standard to prove that the PDE is globally well posed with this noise in this phase space. And more than that, you can prove parabolic regularization effects, continuity with respect to the noise, and continuity with respect to the initial conditions, and things like that. So this is pretty standard. I think the standard references for fluid mechanics especially would be DePrato and Zabchek's book, the one that's called Ergodicity in Infinite Dimensions, and also the textbook by Cookson and Shirikian on 2D stochastic Navier-Stokes. So you can see proofs of this theorem in there, essentially. And from there, you can define the Markov processes, which has to do with the statistics. So you can find a Markov kernel, which tells you, given a set A, what is the probability that your evolution ends in, the evolution of time t is in A, given that you know the initial condition. This is a very nice, well-defined Markov kernel, and it gives you a Markov semigroup. So if you have an observable, which is a function from your phase space to the real numbers, you can say, if I know what the initial condition is, what is the expected value of this observable as a function of time? So that's what this means. And this is a real Markov semigroup because the solution is Markov. Okay, I don't want to get too much into the technicalities, but it's a very well-behaved semigroup. You also get a semigroup on the measures. And you should think of this as, if you randomized, and if you look at this formula, think about it, you want to say kind of what is the, this basically says, if you randomize the initial condition with respect to the some measure mu, what is the probability that you're going to be in a set A at a future time? That's what this formula means. So it's very intuitive. So these two Markov semigroups are extremely intuitive statistical type questions that you want to ask. They do not contain all the information that there is in the system. That's an important thing to know, actually, about stochastics. And we'll see. Markov semigroups do not contain all the information that you might be interested in. The next most important property that we know, and it's actually the only property that we really know independently of nu, the viscosity, which is energy balance. And this is a consequence of Ito's lemma, and it's the random analog of energy dissipation inequality. So you just take the time derivative of the L2 norm, you study the time derivative of the kinetic energy. Or at least in 3D, it's the only thing that we really know if we set nu to 0. And in particular, you can see that time averages of the energy dissipation are bounded. And so you can use this, it's a standard procedure in stochastic PDEs called the Krylov-Bogoliubov procedure. And again, I think the clearest rendition, at least for Navier-Stokes, is probably in Cookson-Shrikian's book. Yeah, I think that's a good rendition. The book by Mine and Tweedy also has a general abstract proof of the Krylov-Bogoliubov theorem. But it's not too hard. Basically, you use the nice properties of the Markov semigroups that I mentioned, together with some kind of a priori estimate that says that you, on average, stay in a compact set. So that's the important thing. You, on average, stay in a compact set. And then you can construct a stationary measure. So what is a stationary measure? This is a measure for which if you randomize, so this is a stationary measure is exactly what we want, which is it's if you randomize the initial condition with respect to this measure, the statistics don't change. Another way of seeing this is on observables. So you can say that this is the ensemble average, and if you randomize the initial condition with respect to this measure mu, the expected value of the observables don't change. Again, each individual solution is changing a lot, right? If you look at water flowing over stone, you see a lot of motion, right? It's not static, but the statistics aren't really changing. That's the key thing. That's going on. So we have them. We have the stationary measures. Now, the next thing you might want to understand is uniqueness. And this is, for the problems that I'm talking about, is also a very much solved problem for the periodic box problem. So if you start adding boundaries, it's very much sort of the best results possible are very much open to my knowledge. But then periodic box is basically essentially completely solved, but it's not at all trivial. So in general, stationary measures are not unique. And that's not something that has anything to do with infinite dimensions per se. So you need some additional properties. You need that there aren't kind of disconnected places in phase space. So one very strong characterization of this is called, what I'll call strong irreducibility, which says that given any initial condition and any open set in your phase space, you have a positive probability of ending up there in the future. So, and I'll just say for all positive time. So I'll just make things simple. That this is all true about this particular system we're studying, but you don't necessarily want to work in such a regime if you can avoid it. Then the other property you need is some kind of regularization, and this could be in many different senses. Some kind of regularization of the Markov semigroup. So you want to understand that like nearby trajectories kind of have similar statistics like in the long term, and this is kind of a subtle, probably definitely the most subtle of the properties to understand that you need. So one really common thing, or at least common characterization of regularity, is what is called Strong-Feller, which says that if I have a bounded measurable observable, then for positive times, actually the statistics become continuous. So think about the case of when phi is an indicator function of a set, right? So then PT phi is literally just the probability that you're in that set, right? And so what it says is that, of course, at time 0, this is, you're either in the set or you're not on the set, right? It's 0 or 1. At future times, what it says is that PT phi, if you're Strong-Feller, then it's now a continuous function. So it gets kind of smeared out. So now there is no sharp boundary of being not in the set or not on the set. It's clearly something that uses the noise, right? Because if it was a deterministic evolution, you would never change that fact, right? You're either in the set or not in the set as a function of time, right? But here it's like, okay, nearby trajectories, like this guy will have like a 50% chance of being in the set, and this guy will have a 51% chance of being in the set, and so forth. That's what Strong-Feller would mean. Okay, so it's a regularization property, and indeed, you can use, in finite dimensions, you use parabolic regularization or hypoelliptic regularization to prove things like this. In finite dimensions, we basically completely understand how to prove Strong-Feller, and it's quite common in systems, in finite dimensional SDEs. But in infinite dimensional SDEs, seems to be very uncommon. These two properties together is enough to prove uniqueness of stationary measures. So this is a famous theorem called the Dubh-Kedzminski theorem, I think that the best rendition of it is in DePrato and Zamchek's book. Actually, these two properties tell you a lot more than just uniqueness of stationary measures, which is a much weaker property than these guys. Because of our conditions on the QKs, actually these properties are true in our phase space. So our Navier-Stokes equations is going to satisfy strong irreducibility. That's actually the easy one to prove. And it's actually strong Feller in our Sobolev space H. That is way more than you need to prove uniqueness of stationary measures. So Higher and Mattingly show that you can prove uniqueness of stationary measures, certainly without strong Feller and in much more general classes of forcing. And it uses Malevin calculus. And so for those of you who don't know, Malevin calculus is basically differentiating with respect to the noise path. So if you have a noise path omega, then you want to know the dependence of the trajectory if you kind of disturb the noise path a little bit. So you want to infinitesimally distort the noise path, and you want to understand how the solution itself changes with respect to that change. In that regard, it is as cool as it sounds, but it's not as hard as it sounds. So it looks rather intimidating from the outside, but it's neither really hard nor counterintuitive, I would say, once you get used to it. And I would say once you think about it, it's not too hard to see why it's closely related to regularization of the Markov semigroup, because you really want to understand, how small changes in the noise could make small or large changes in the trajectory. Okay, so it's a great open problem to sort of extend everything that I'm going to talk about today to the regime of Higher and Mattingly. I think it's quite hard, but if you're looking for a challenge, perhaps. So for now, I'm going to work in this framework. We're actually going to have strong Feller. Okay, in this framework, where you have strong Feller and you have a unique stationary measure, that's great, right? Because now the Pointwise organic theorem tells you that all the initial condition actually converges. In fact, you can prove using strong Feller that every initial condition, not just mu almost every, you can actually prove that every initial condition in the phase space satisfies this property almost surely. So time averages equal ensemble averages, and you can prove that this, the stationary measure is supported everywhere, essentially. So everywhere, every open set, the stationary measure assigns positive probability to that. And so this kind of observability thing and the uniqueness of ensemble trajectories is solved. And all of this stuff had nothing to do with our work, I should say. This is all classical with this type of forcing. So with other types of forcing, more general classes of forcing, there's still research being done. All right, so now that we have like a qualitative framework done, so there exists a unique stationary measure, mu nu, and we want to understand things. So in terms of turbulence, and this isn't specific to 3D or 2D Navier-Stokes, just you have a turbulence system where you have a unique stationary measure. The whole question really is what happens when nu goes to 0, the dissipative parameter goes to 0. So the first thing you want to see, is it chaotic? So you want to understand if nu is small enough, if the dissipative parameter is small, do you have a positive Lyapunov exponent? And does it diverge, for example? The next thing you want to know is, do you see this anomalous dissipation effect? And this is not phrased super mathematically rigorously here, but it's not too hard to phrase mathematically rigorously for a lot of specific examples. And then you want to understand, so if you know those two facts, or even just the second fact, you could then ask, how does, for example, the energy distribute itself in the inertial range? And also, where is the inertial range? So you want to understand how big the inertial range is as a function of nu, and how does the energy distribute itself? And then if you have something like that down, you can even potentially try to pass to the limit and construct kind of like a weak, sort of like a statistically stationary version of those convex integrated wild solutions. They're kind of a constant in time anomalous dissipation at the inviscid level. And then you can just keep on layering harder and harder things. The point is that I would say basically all the questions about turbulence can be phrased mathematically rigorously without too much trouble in this framework. So any question, you ask, or the physicists predict X, or the physicists predict Y in the experiments, or we measured this experiment and they got this power spectrum. It's not it's not unclear how to phrase this mathematical conjecture, phrase this as a mathematical conjecture. What's extremely unclear is how to prove it, let's say. And so the question is, can we prove anything on this checklist for any model? Or any model in physics, at least. So there are some simpler, kind of very simple shell models, not as complicated as the ones they really use in physics, for which you can prove this, actually. And that already is interesting work, I should say, by Glattholz, Freelander, and Fiegel. And then there's a paper by Jonathan Mattingly and a collaborator who are also using a kind of toy shell model. But let's talk about a physical model. And so the physical model that we can study is what's called passive scalar turbulence. And so we're going to solve the Navier-Stokes equations, again, with stochastic forcing. And then we're going to solve this secondary equation where G is a scalar. And it's also going to be subject to a stochastic forcing. And independent stochastic forcing is very important. And then we want to understand not what happens when nu goes to 0. We're going to basically fix nu. And we're going to send kappa to 0. So this is actually, I should say, this is a specific regime of passive scalar turbulence. There are more general regimes if you send nu and kappa to 0 in sort of different ratios and stuff like that. Those can be extremely hard problems and we have no idea how to study right now. But if you fix nu to be like 1 or 0.0001 or 10 million or something, doesn't matter, as you'll see. When you send kappa to 0, this is a statistical problem in statistical physics, essentially. Or statistical theory of turbulence, shouldn't say statistical physics. And G here, think of it as a temperature variation or salinity variation. And this is what you expect to observe. So here the numerology is in 3D because it's simpler. And so the dotted line is what you see in experiments for the fluid. So this is, again, it's a log-log plot for the power spectrum. And so here's the injection scale. There's no universal theory for that. It's just whatever it is. And then here is where the fluid is turbulent. We have no idea how to study that. That's another regime of passive scalar turbulence called Markov-Corson theory. Very interesting. No idea how to study it yet. And then at the dissipative scale of the fluid, which we have no idea where it is because we haven't solved the turbulence problems for 3D Navier-Stokes yet. At some point, though, if kappa is small enough, the fluid is kind of smooth, or looks smooth at least at those scales. And but the scalar is still dominated by the nonlinear transport. It's still dominated by this term. And it's nonlinear in UG, which is actually the unknown, the system. The coupled UG is the unknown. But it's linear in G. That's one of the reasons why this is the simplest sort of physically relevant turbulence theory to study. So if you look at small enough scales, you enter what's called the Batchelor regime. And there, what's expected and observed is a specific power spectrum of exactly -1. And that actually is, well, if you scale it correctly, that's independent of dimension. Okay, so that is the regime that we're going to prove. So that's what we want to prove. Okay, and that's what we have succeeded in proving, Alex, Sam, and I. And okay, so there is lots of, so physicists have been observing. So Batchelor, I should say, Batchelor predicted this kind of semi-analytically using, well, he basically predicted using a toy model. So he said, look at this toy model. This toy model suggests this is the right power spectrum. And he did that in 1959. And I'll show you a sort of more accurate version of the toy model, but his toy model was, well, it was right, as you'll see. So his prediction is correct. Physicists and engineers started measuring this very quickly. So this is measurements from the ocean. So they just dumped sensors over the side of their boat. And this is basically the measurement version of this slide. So this is the fluid. And there you see the 5/3 power spectrum. So this is the 3D Navier-Stokes. And this is the scalar. And this is the Batchelor regime. And this is a salinity variation in a controlled laboratory experiment. And again, this sort of fluid, and then this is the Batchelor regime. And you have some, a bunch of computer simulations where they tried to check this and understand this. So let's see. So then, when we set out to try and prove this power spectrum, we wanted to say, all right, what is why is it -1? And so we came up with this toy model to convince ourselves that this is actually the correct answer. And also sort of this is going to be kind of how we prove it in a sense. So one thing that physicists have learned is that the Bachelor spectrum is so kind of universal that it doesn't even depend on the Navier-Stokes equations. So it's true for a bunch of things, not just the Navier-Stokes equations. That's the first thing to observe. And so we can come up with a simple toy model that displays this power spectrum in some sense at least. So what we're going to do is we're going to replace the fluid transport, sort of advection term, with kind of a toy model for transport, which is going to be the Arnold cat map on the torus. So what you do is you map, so at every point on the torus, you map forward with this matrix, and then you mod it back to the torus. And this is sort of the canonical uniformly hyperbolic map. So it's kind of as chaotic as it possibly can be. And that's kind of going to be our hint. And it satisfies one more really important property that makes the toy model very simple, and also makes this toy model pretty similar to what Batchelor proposed as well. And so what I'm going to do is I'm going to do this time stationary problem. I'm going to forget about the dissipation because that shouldn't change the inertial range statistics. And so every time step, I'm going to dump in a random amount of scalar at scale 1. So that's my injection. And then I'm going to map the scalar field forward by one iteration of the cat map. Now, because the cat map maps Fourier modes to Fourier modes, and that's the key property that makes this solvable, I can just figure out what the solution Gn is. And it's this particular random Fourier series. And A inverse transpose has an eigenvalue which is bigger than 1, and an eigenvalue which is less than 1. And I've chosen this vector so that it lines up so that this frequency is basically exploding exponentially fast. Okay. So what you get is you get frequencies which are very sparsely supported in Fourier space. So basically you have one every lambda at x shell. You have one frequency that's on and everything else is off. So it certainly doesn't satisfy Batchelor's law kind of pointwise in frequency. But if you average over dyadic shells, what this tells you is that you have about order 1 energy every dyadic shell. And Batchelor's law is precisely the prediction that you should have 1 over k to the dimension energy as a function of k, which is the same thing as saying each, or not the same, but kind of in an average sense, on average, each dyadic shell contains about order 1 energy in the inertial range. And so that's the toy model, and that's also going to be a hint as to how we're actually going to prove the theorem. So the key point in this toy model was that low frequencies went to high frequencies exponentially fast, and that's what we're going to that's how we're going to prove it for passive scalars. So this is the real problem at hand, let's say. And so just to simplify our lives, we're just going to apply a 1D Brownian motion to the scalar. It doesn't matter. You can use a bunch. It just doesn't matter. So just pick any mean zero function b, which is smooth or whatever, and apply a 1D Brownian motion. So this is going to be my injection. It's not hard to prove that there exists a unique stationary measure to this problem. And so for every kappa, we have a stationary measure mu kappa. And the idea is we want to understand the statistics as kappa goes to 0. And so this is the theorem in our final paper on the topic, final for now anyway, which says for every fixed nu, there is a scale n0, after which you see the universal Batchelor rule, Batchelor law, in an average sense. So now we're not just averaging over shells, we're also averaging over balls. And so if you average over balls, you should see log n. And so you have a constant independent of kappa above and below where you see log n growth. And that goes from a fixed n0 all the way up to kappa inverse, kappa minus 1/2. So that n0 is So if you think back to this thing, n0 is this line. Of course, we have no idea what that is as a function of nu because we don't understand turbulence in the number of Stokes equations yet. We're studying this model not only because it's much simpler, but it's much simpler. And you have to understand the simple versions. I would assume you have to understand the simple versions before you can understand the harder versions. Once you have this theorem, you can kind of build off of it and actually pass to the limit in this problem. So you can pass to the limit and construct stationary weirdo distribution valued solutions to this problem. And this is weird, right? Because this is smooth. This is pretty much smooth. Whatever. Or you can come up with examples where that's smooth. But G is still violating all the conservation laws. And so G, of course, can't be even LP integrable because that would violate kind of conservation of L2, for example. And so they're crazy distribution value. And that's actually what you expect. That's what Batchelor predicts. So it's not in contradiction at all with what physicists observe. And you get kind of in the inviscid limit, you get this energy flux through scales. So you get this limiting weak solution satisfy this. So this is frequency projection to scale less than n. And so you see this is kind of energy flux. And the energy flux through scale n asymptotes to something constant, just the L2 norm of b squared, basically. So you have an energy flux that's constant through the entire inertial range, basically, for all frequencies. And you have this Batchelor's law at all scales. And this is, again, what you expect. So this kind of actually satisfies, and you'll see in some sense, this checks this, and this bullet off for passive scalar turbulence in this specific Batchelor regime. In some sense, you'll see we're going to check this off, kind of. It depends what you mean by that. And that's actually an extremely pivotal step in the proof. This, we have no idea right now. So still not done even for this simplest case. There's one more sense in which we get a constant flux of, I'm not sure this is, only if you're a real buff into reading physics literature is this exciting. But I would say that before Batchelor's law, there was an older universal law called Yaglom's law. So I would say, so you remember how I said that every turbulent system has this property that you have a constant flux of conserved quantities through the inertial range. But in fluid mechanics, it's actually so here this is sort of like the Fourier version of that. In fluid mechanics, it's a classical way of re-expressing this energy flux through finite differences of the velocity fields or the scalar fields. And this was actually Kolmogorov's in some sense, most central prediction in his 1941 papers. So historically, it's really important to study these laws. They're not, from a practical perspective, they're not as important as the power spectrum at all. And they're much easier to prove, at least in this one example where we have a proof. So this universal scaling law was proved in our first paper, and this was proved in our fourth paper. So it's much harder to prove the power spectrum than it is to prove anomalous dissipation in this sense. The statement's kind of complicated. I don't think I want to get into it so much. But just so as a heads up, there are other universal laws that you may want to prove that quantify anomalous dissipation, and these are definitely easier than understanding the power spectrum. So the Kolmogorov-Forfitz law is definitely almost definitely much easier than understanding the power spectrum of Navier-Stokes, for example. This is actually a good time to take a break. So whenever you guys want me to come back, basically, I can come back.